So while we're waiting for folks to come in, I'd like to thank the sponsors of breakfast this morning, the Power Breakfast. As my parents always say, happy hour is the most important meal of the day, but breakfast is number two. So the breakfast sponsor was Arbor, GDT, and LinkedIn. So thanks to those folks for giving us a really nice breakfast with plenty of bacon. Our break has been sponsored by A10 Networks, Approved Optics, and Avaya. Personally, I'd like to own a company called Disapproved Optics and see how that goes. I like that, Approved Optics. A couple other announcements. Now that I'm up here, please turn off your cell phones. It's just very distracting for the speaker, so make sure they're silenced. I don't want to hear anyone's Gangnam style ringtone. Our first speaker this afternoon is going to be Cameron Byrne. He's going to be talking about, I don't know how you actually pronounce it, 464 XLAT or XLAT. And it's another one of those cool IPv6 transition mechanisms. And Cameron, of course, is one of the experts on the IPv6 transition. So without any further delay, let's go to Cameron's slides and take it away, Cameron. Thank you.
So thanks for having me here. My name's Cameron. This is the most important slide probably. It is the slide with my email address on it. So if you have some questions about what we're talking about today or T-Mobile in general or anything like that, I try to make myself available to the community, to support. We're a big part of the internet, so we want to have a role there and be accessible. T-Mobile is a local company here in Bellevue, so this is our home turf. Welcome to Washington. So goals of the talk, pretty ambitious. We'll start out with declaring victory for IPv6. Some people have more victory than others. The people who tend to deploy V6 have more victory. So more V6, more victory. I'll explain how we did IPv6 only at T-Mobile, and why IPv6 only is an important attribute of our solution. And then we'll talk about how, if you have millions and millions of phones on V6 and you run an important mobile optimized website, you may want that website to be on V6 as well, because we're going to send your V4 only applications and V4 only content through some hoops to make it work. And you'd rather not go through hoops. You'd rather have end-to-end proper IPv6 internet. So here's a lot of text. I have more slides than minutes and a lot of words here. So this is on purpose for the sake of the archive. So I want to make sure that we have a lot of information here, but I don't expect you to read it right now, and I won't read it to you. But the overall background is that T-Mobile has about 50 million subscribers. We're a GSM UMTS LTE provider here in the United States. In 2008, we had the crazy idea of launching the first Linux phone, right? Linux on a phone, ha 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 ha, right? Oh, Android, it's really big, and that's Linux. And when we had that, initiative, when we had that launch, the dynamics of mobile phones changed dramatically, right? The bad old days, you had your Motorola Razr, you're real cool. Popped it open, downloaded a ringtone, got an IP address, closed it back up, put it back in your pocket. And when you put it back in your pocket, it gave back the IP address. Now with phones being always on, they're always holding IP addresses. And if you have 50 million phones, they need 50 million IP addresses. So that wasn't going to work for IPv4. So at that point, we decided, we needed to have a better solution than RFC 1918, what we could get from Aaron. We needed something better. And so IPv6 is the obvious answer. So we're like, great, let's do some IPv6. And then everybody told us, you need to do a dual stack, because that's how you do IPv6, you do dual stack. And then we said, wait, we don't have IPv4, so we can't do dual stack. We need to do something that actually scales, that actually solves a problem. So if you have a problem of having more endpoints than IPv4 addresses, dual stack is not a solution for you. You need to have something better, right? Something that's IPv6 only. So we look to find ways to decouple our scarce IPv4 holdings from a quickly growing network edge of mobile computers, mobile phones, sensors, all kinds of interesting things that people want to connect to a mobile network. So we stumbled upon NAT64 DNS64. This is a method for connecting an IPv6 only endpoint to an IPv4 internet. We said, great, that's exactly what we want to do. So we started testing that, and then we realized a lot of things didn't work. So that wasn't going to work just as we had planned. So we were like, okay, well, what doesn't work? Okay, Netflix and Skype doesn't work. Well, we don't really like Skype anyways, right? We're a big telco. So, we'll let that go. And we told ourselves that for a while, but then, it dawned on us that Skype's a top 10 Android app, and we're not going to win any friends with customers, most importantly, by not supporting Skype out of the box. So then we went and said, okay, well, is there something we can do to patch NAT64 DNS64 solution that we like a lot because it decouples those, those endpoints from our IPv4 holdings? Is there something we can do to fix that? And so we went about and said, okay, talked to some folks in the IETF, and it was going to be an uphill battle, but eventually we were able to put a NAT46 in the handset that would send IPv4 traffic to a NAT64. And this is terribly ugly and tremendously unpopular, especially in the IETF, but we had a use case and we showed that it worked, and it solved a very specific problem. It solved the specific problem of most things work in a NAT64 DNS64 environment. But there were a couple of sticklers that weren't going to, I had no control, and I still have no control to make Skype work on IPv6 or Netflix or Spotify or WhatsApp or any of these other really important applications. There's nothing I can do to say, hey, fix your stuff, right? So we had to put in a shim in the IPv6 stack, which is called the client translator, the CLAT, that would present an IPv4 address to the network stack on the host, and it would in turn translate that IPv4 sockets into IPv6 packets that would flow out of the network. And we'll go into that in more detail. But the long story short is that we got this into Android, we got this documented in the IETF, and we launched it in October 2013. And all 4.3 Android phones at T-Mobile going forward will be IPv6 only. So we have a lot of IPv6 users now. Results are important, right? So this isn't a theoretical exercise. This is a big network with a lot of endpoints. So we've launched 8 Android phones that are IPv6 only out of the box today. And as I said, our strategy forward is IPv6 only. To date, we have 8 million subscribers that are on IPv6 only. There's 8 models. Grandma pulls the phone out of the box, opens it, powers it on, it gets an IPv6 address. Great, right? A lot of things work. 27%. So ISOC measures IPv6 connections as part of their World IPv6 launch website, and I'll cite some more of that stuff later. But 27% of the connections from T-Mobile going to dual stack websites is IPv6. And for our IPv6 users, over 50% of their traffic is IPv6 end-to-end. So we talked about how 464xLAT's not terribly pretty. It's a double translation solution. NAT64 is not particularly pretty. It's a translation solution. But the fact is that Netflix, YouTube, Google, Facebook, a lot of important content on the internet is end-to-end IPv6. So these transition mechanisms, especially the less desirable ones of double translation, is really a corner case. And as time goes on, that corner case is going to get smaller and smaller, and the end-to-end IPv6 will get larger and larger. So here's the World IPv6 launch website. So as you can see, we're very proud of these numbers. In 8 months, we are up to 27%. We're not alone. The IPv6 edge networks are large. Comcast, AT&T, Verizon Wireless, Time Warner, all substantial growth. Verizon Wireless, yes, that's 50%. So every now and then you'll see on the NANOG mailing list, Jared or somebody saying, oh, I only got 0.01% of my backbone's IPv6. But those places may not be exposed to my eyeballs, these eyeballs, or some of those big content players like Google, Facebook, Netflix, Yahoo, Wikipedia. All these are really important things that are on v6. So we certainly see it. So a little bit more specific about the 464 cloud. So, as I said, we couldn't do dual stack. It didn't solve a problem for us. So we had to do something that was IPv6 only. NAT64, DNS64 were short. They worked for a lot of things. I could still get to Amazon and Twitter. And their IPv4 only websites worked fine via this translation solution, but Skype and things like that didn't work. So we had to solve the numbering problem. We had to present an IPv4 address to the stack. We had to decouple our endpoints from IPv4 holdings. There's a couple other IPv6 only solutions out there based on tunneling, such as MAP and DS Lite. Those really had the terrestrial networks in mind, like a DSL or a cable network that already had a substantial DHCP deployment. Both of those solutions heavily rely on DHCP. Mobile networks, 3GPP networks, don't use DHCP at all. So they're really not really an option for us. And getting DHCP into those networks wasn't going to be easy because essentially it relied on, with NAT64, DNS64, with 464 XLAT, I could cooperate and submit patches to Android to get them fixed, to get the features I needed. Ericsson and Nokia, Siemens, they're not going to take a patch from me. They'll give me a bill and probably be late, so I had to move on without them. So IPv6 is, for us, what was achievable, but it took time. It didn't take money. We didn't spend money buying a bunch of new gear. This is actually really a zero CapEx solution. The only thing that our project billed for was a QA process of sending IPv6 addresses through our billing system. We did a lot of innovative thinking. People could say, okay, well, to deploy IPv6, you needed to do dual stack, you need to do all these things, and there's this whole rigmarole, right? One of the interesting things is, for example, when you attach the network, it sends a call detail record, which flows through our billing system, and it carries a 32-bit value, which is your IP address. That value has no meaning in our billing system. And to update the billing system to accommodate a 128-bit address instead of a 32-bit address was estimated to be between $5 and $10 million. And for a project that has essentially zero funding, we're like, well, that's not going to work. But we knew a guy who essentially pre-processed the CDRs. So he would sanitize the data before it goes into the billing system and starts flowing through. And he said, yeah, I can just hash these numbers from 128 to 32 bits, and they're not used for anything, so it'll just flow through the system. You don't have to upgrade anything. We're like, yeah, win. So we did that. So if you want to spend a lot of money on IPv6 transition, you can, but there's probably a lot of other ways around it to get the desired result. So where are we today? Platforms, Android 4.3 and forward support it. That's great. That's the vast majority of it. Of what we do. What's not supported is BlackBerry, Apple, or Windows. We hope they support it soon. So we'll do a brief technical walkthrough of exactly what it is that we've deployed here. On the handset itself is a stateless NAT64. So what this means is that we translate all of the 32 bits in the IPv4 routing system into the lower 32 bits of an IPv6 packet, and there's an algorithmic translation mechanism there. Stateful NAT64, it's a whole lot like NAT44, but with 6 on the inside and 4 on the outside. DNS64, this is something that folks who aren't aware of it get interested in that in my network there are Quad A records for IPv4 only websites. Like if you do a Quad A query inside my network for Twitter or Amazon.com or Bing, those are IPv4 only websites in the real world, but in my world of my network, they have Quad A records. Why? Because I make them. My handsets query for Quad A records and they get it back, and that's a synthesized DNS record that I have created on the fly based on their IPv4 A record, and that DNS64 shoves the traffic through the NAT64. So it's from my perspective, it's a pretty clever solution to having an off-path control of a IPv6 flow, an IPv6 flow that terminates on a NAT64 and then reinitiates on a NAT44. As I said, we don't run any sort of DHCP and 3GPP networks. It's just not something that's done. So we had to discover where the NAT64 was, right? So a lot of the scenarios that we had to deal with, a lot of the problem scenarios were things like Skype. Skype didn't use DNS. It got your buddy list, and your buddy list has an IPv4 address that's associated with your buddies, right? And it sends a IPv4 packet to your buddies. DNS isn't involved. So if there's no DNS involved, then I can't send you to the NAT64 for translation. So the prefix 64 discovery is a method for finding where the NAT64 is, informing the stack of the handset so that the handset can send IPv4 packets to the NAT64 without the need of the DNS64. This is a bunch of words. Here's a pictures of what those words means. So at the end of the day, I have deployed pure, simple IPv6 as the high priest of IPv6 had intended. So that's the smiley face one. So everything that smiley face is your Netflix, it's your Google, your Yahoo, your YouTube, Wikipedia, all those great things, Facebook, ton of traffic. Ton of traffic falls in that top category of IPv6 end-to-end. It's a beautiful thing. The second most popular solution is your IPv4 websites, your Amazon.coms, your Twitters, your Bings. These guys haven't embraced IPv6 yet. They're hopefully going to do a great job real soon. But in the meantime, I'm producing quad A records for them and sending them through a NAT64. They don't get a smiley face. They're good enough. There's a handful of things that are important that fall into the third category, which is least desirable. That is the scenario where I'm going to NAT46 your traffic on the handset, send it through a NAT64, and then send it out to you. So that's the WhatsApps and the Skypes and things of that nature. So they're really not a high bandwidth scenario, not a lot of things, but we can't break them. So stateless NAT64, the whole idea here is that it's not dynamic, it's deterministic, and essentially maps all the 32 bits of the IPv4 routing into an IPv6 prefix. So as you can see there, you got an example prefix, you stuff a 32-bit IPv4 number at the end of it, and essentially that's how you signal to the NAT64 saying, I am going to send you this packet, you need to decode the last 32 bits and then pass it on as an IPv4 flow. Stateful NAT64 is like NAT44 in the sense that I'm still sending traffic to the CGN, to the NAT64, but instead of a deterministic algorithmic mapping, it is a dynamic. So just like CGNs and IPv4 that we know today, it maps the source that it will send to the IPv4 internet dynamically from a pool of addresses. And we talked about DNS64, so the whole story here is that Amazon.com doesn't have a quad A record, so I am going to make one for them. I'm going to take the answer from their quad A record, and I'm going to synthesize I'm going to take the answer from their A record and create a quad A record that routes their traffic through my NAT64. Here is a diagram of how that flow works. Here's another diagram of how so that last diagram was the canonical NAT64, DNS64 method. This is a diagram that Dan Drown made, and he did a lot of the initial prototyping, a lot of the initial idea of this. And the story here is that you have an IPv6 lane and then you have an IPv4 lane. And when you have an IPv4 socket that's being formed, we're going to run you through this CLAT daemon, which is going to do the algorithmic stateless NAT64 on the handset, and then send it out to the NAT64 in the network. So this kind of shows hop by hop how things change in the different functions within this architecture. So we'll zoom out to this protocol land and kind of look at what it looks like in a mobile network, right? So mobile networks, you have your handset over there to the left, and then you have a radio access network, which is largely sort of, you can view it as a layer 2 network. So all the cell sites and things like that have a layer 2 nature to them. And HLR is a subscriber database, so that tells me what subscribers are authorized to be on my network and what they're allowed to do on my network. The reason why it's on this diagram is because initially all my subscribers were allowed to do IPv4. I had to update every customer record and say, you are now doing IPv6 as well. So all the subscribers can do IPv4 or IPv6. And that's kind of the philosophy that we took to this deployment is, let's the subscriber deploy. We choose, right? So any subscriber can do IPv6, any subscriber can do IPv4. We're setting the default to IPv6. The GGSN is kind of like the aggregation node, like a BRAS or a CMTS or something of that nature in other architectures. So that's where the IP packets that the phone forms, that's where they actually hit the wire. So on that interface, they hit the wire, and that's where we put the NAT64 and the DNS64. So those are the things that needed to change in the network. Zooming in on what a handset looks like, if you go into the APN configurations of mobile network, you will see this APN protocol is IPv4, IPv6. All of our Android 4.3 plus handsets going forward are set to IPv6. There's no button for 464 XLAT or anything like this. Android's set up so that if you choose IPv6, you are getting 464 XLAT because IPv6 on its own is not terribly useful, so we'll just give you this one option and we'll kick off the processes for making 464 XLAT happen. So here's an eye chart for you, but the basic idea here is that this is what it looks like on the wire. Just like anything else, we start with DNS, do a DNS lookup for whatever we're trying to get to. If it's an IPv4 only resource on the internet, we'll create a quad A record for it. And you see that the quad A record is simply my prefix 64, which is the destination of my NAT64, and then I take the 32 bits associated with the real A record, and I come up with this 32 bits of hex that I put at the trailing end of the prefix 64 there. So the first 96 bits say this is the NAT64 I'm sending you to. The last 32 bits say this is the IPv4 resource you're trying to get to. And when it gets to when this packet gets to the NAT64, the NAT64 strips off the first 96 bits, decodes the last 32 bits, and says, okay, you're actually trying to go to this 32-bit IPv4 host. So next, the UE gets the quad A DNS, and then it starts IPv6 TCP, and it goes off just as you would expect it to. This is, from the handset's perspective, this is just an IPv6 resource. They don't know it's NAT64. They've been completely tricked. There's no special code to make this work. This is just a normal IPv6 endpoint. In the middle, I created a quad A record for a resource that doesn't have a quad A record on the internet. So I've tricked the normal IPv6 handset into thinking that Twitter has IPv6. There's a less desirable case. So this is the third case that we've talked about of translation on the handset. And this is actually the worst of possible cases because WhatsApp creates a very large resource set. So when there's a very large 32-bit resource set and then you blow it up to be a 128-bit quad A resource set, it becomes a TCP DNS query. Oh, Android doesn't support eDNS 0. So now by being IPv4 only, not being able to do IPv6 sockets, and having a really large DNS response, they're in a non-ideal performance situation. Okay, so what happens here is that WhatsApp is not able to send a IPv6 socket. It's not able to process a quad A record. So it only gets an A record back. That's what we saw on the last slide. And this slide says, okay, well, I can handle A records because on the handset, I can bind an IPv4 socket to this dummy IPv4 address I have on this client, this CLAT interface. And we can see it here on the wire. The source here is the 464 address. So that's how we know that this is coming out of the translator on the phone. But that doesn't happen that often. We go to the Alexa top 10, Google, Facebook, YouTube, Yahoo, Wikipedia, all pretty good, right? That's a lot of resources that are on the internet that are delivering a whole lot of bits on IPv6. So when we look at those less desirable translation scenarios, and really that's, they're not that huge in scope. There's a lot of eyeballs on v6. So you go to that World IPv6 launch website, they update it every month. There's a lot of eyeballs there. There's a lot of content there. So when people say v6 isn't there, I say, well, I'll show you the largest edge networks in the United States, and they're there. I'll show you the largest websites, and they're there. So folks that are on IPv4 only solutions, you're kind of finding yourself in the long tail. I wish you would be on IPv6. And then, we have this thing coming up where Internet of Things, and they need a lot of IPv6 for sensors and good stuff like that. And people have multiple tablets and phones and all kinds of interesting. Another thing is that voice over LTE requires an additional IP address on the handset. So if there's any, so the whole voice over LTE solution is a 2 IP address solution. So you need the IP address that you use for default for internet, and then you need a separate IP address for voice over LTE. So that's another interesting case I see driving a lot of IPv6 in mobile networks is that as they move into packet voice over LTE solutions, they need to be IPv6 because you just can't double the number of IPv4 addresses you have. So we did something different here at T-Mobile. We went an IPv6 only solution. We have 8 million subscribers on it, so we know it works. We'd never done anything in the IETF before, but I think this is a pretty good case study in an operator who's never had a problem or need to go to the IETF, had a problem, went to the IETF, got some work done, was able to document a solution, was able to get patches in Android, and was able to essentially solve an operational problem. What didn't work is saying, oh, let's just go break Skype. That's their problem. That's their broken app. And a lot of people say that, right? But the reality is you can't screw over your customers. It's not a good idea. I don't recommend it. Even if their app is broken. Question the answers. A lot of people tell you, or have told me, that dual stack is the way you deploy IPv6, but if it doesn't actually solve your problem, you should probably try again. We can't boil the ocean. Tethering is still IPv4 for us due to various problems. And we didn't go and try and convert everybody's phone to IPv4. It's a per phone model solution, right? So as we release new phones, the new phones get configured as IPv6. We're not trying to update everybody's Motorola Razrs from 2005 to be IPv6. And the summary is that it was a pretty good solution. We're pretty excited about it. We're growing very quickly, and we're happy to be growing out of NAT, right? A lot of mobile is NAT. A lot of mobile is CGN. And the 464 XLAT solution, the NAT64 solutions in general, allow you to increase your IPv6 exposure while decreasing your NAT exposure, right? As more and more content comes online as native IPv6, the content, the bits that need to go through NAT64 decrease over time, right? So we're going to ride that curve, and we're going to get to a point where a very trivial amount of traffic is on IPv4 and requiring a transition solution. So any questions? Yes.
Okay, Louis Lee, Equinix. Thank you for this presentation. It's really interesting. Being that it's a solution that works only on your cellular interface, is there, I'm trying to think that maybe you would have an advantage in getting something working well on the Wi-Fi interface too for when the users, say, home internet connections start being V6 only. If if your handsets and your tablets are able to use their V6 home internet and not any of their other devices, why not do T-Mobile, for instance? Is there any thinking beyond just your cellular interface, like try to do a Wi-Fi interface or even your Bluetooth interface?
So you're talking about like a tether solution? Yeah, so we're, tethering something that we're working on, but, we had to create a set of priorities, in terms of, this is the primary consumer of IPv4 addresses on our network is handsets sitting in people's pockets. So that's if we can transition those from V4 to V6, there's a huge upside. When somebody takes their phone and connects it to Wi-Fi here at NANOG, they drop the T-Mobile interface. So they're no longer consuming a T-Mobile IP address. And so I'm just like, great, because I'm just managing my own scarcity, right? The handsets we sell, by and large, support Wi-Fi. So if the Wi-Fi supports IPv6, they'll get an IPv6 address. But what we're really managing is nodes connected to our network and managing our own scarcity. In general, we want to try and support as much IPv6 momentum in the world as possible, because more IPv6, there's a network effect, and it's a great thing.
Yeah, I understand. In a big way, it's not your problem anymore once they're on the Wi-Fi network.
Right.
But the user unknowingly will still blame you if their device doesn't work at home.
That's a risk we run.
Yes, be aware of that coming.
Yeah.
Ralph Mullen, Internet Archive. In the case of Skype or Skype-like protocol, if you and I are on the same cell site and I want to send you a file, do those bits have to go out to the public internet, or is it handset to base station to handset without ever leaving your local loop?
This thing doesn't go back so well, but the answer is that this thing called the GGSN, we have these in NFL cities. So, anybody in a tower, on a tower, their IP address and all their IP communication aggregates up to a routing within this GGSN. So there's never any cell site user-to-user communication. You always have to roll up to this device, which is your mobility anchor. That pops you out as an IP packet, and it may just do a U-turn in that device to go back out, but it's going to roll up to this NFL city type deployment where these GGSN nodes exist, and that's where the real IP routing happens. Between the cell site and the GGSN, it's a point-to-point layer 2 network of sorts.
Ethan Katzbass, University of Southern California. That was an interesting talk. I just had a small question. I didn't quite follow the WhatsApp DNS example. Do you mind just explaining what it would have looked like if you had been doing V4 to them? Like, I didn't quite follow what was going on there. So
Okay.
can you just walk through it once more?
Let's see. Boom, boom, boom. Okay, so WhatsApp sends a very large resource record with many A records in it and stuff. And what happens is that my DNS64 receives that very large resource, very large DNS response with all those A records in it, and it translates them into quad A records. So the 32-bit values now become 128-bit values. And when they're 128-bit values, they can go over 512 bytes, which is canonically what the max UDP DNS response is. And these handsets don't support eDNS0, so it's really 512 bytes. And when it's over 512 bytes, then it falls back to TCP, and then you have to do a TCP three-way handshake. So the long story short is that WhatsApp isn't optimized for my scenario, and I didn't optimize for them. My hope is they'll deploy V6.
Got it. That makes sense. Thank you.
Jeff?
This is kind of a hypothetical question at this point, but it's sort of the what if, that if this was extended into Apple's iPhones and iOS, and this conversation with Louis Lee about Wi-Fi is Wi-Fi and the wireless is the wireless, but it's not anymore, because on my iPhone with multipath TCP, I start off in one and then open up a connection on the other. And my question was, but hang on a second, down the wireless, not the Wi-Fi, but the 3G, 4G, whatever, I've got this faked DNS. Mm-hmm. But what happens when I then go down a multipath route and think that the Wi-Fi will handle the same address.
Yeah, it's not going to work. Because my NAT64 is not
so
available to you and the general public. It's
Why
available
is
on my
it
network.
that, you know, over on one side of the industry, we start deploying technologies that make particular assumptions about behaviours, and Apple have done with multi-path TCP. And over the other side of the industry, we're forced into making contradicting assumptions.
It will work perfectly fine as long as the endpoint is IPv6 enabled, right? Because I only screw with the IPv4. IPv6 is the pure religion,
Thank you.
and it's the true end-to-end internet.
We're gonna close the microphones after these two questions. So over here.
Phil Rosenthal from IS Prime. So actually a related question. So when you're generating these Quad A records for IPv4 only hosts, like I understand, you're saying IPv6 is what should work, but you'd like to avoid breaking v4 where possible. So you're spitting out a v6 address for something that doesn't actually exist, and the user switches from using cellular to Wi-Fi. They get home, it connects to their Wi-Fi. That application may start saying like, okay, I'm going to try and send connections to that v6 address. Say the Wi-Fi supports v6, and now that v6 address doesn't exist on their Comcast service at home. So that connection may just not work at all. Have you done anything in particular to like make it so that the DNS entries expire? Or
Yes, absolutely. When you change from the cell network to the Wi-Fi network, the DNS is flushed on the host. If the app holds on to that, that's kind of their own problem, but from the network perspective, the DNS is flushed. And obviously, there's no multi-homing in Android, right? So whenever you move from one network to the other, you're completely wiping the network stack. You're starting all over again, so there's no persistent connections from a stack perspective.
And is this something that Android is doing as standard for like if anybody wanted to, or a custom thing for you?
No, this is straight Android.
All right. Thanks.
Yeah, I'm Eric Rosenberry from iOvation. I had a question around when you're doing the 464 XLATE, you're using a dummy IPv4 address on the phone. Is that an RFC 1918 or is that in public address space?
That is an address that is currently allocated to DS Lite. So it's 192.0.0.0 through 7, I think, is the range. And so that's reserved for DS Lite. And then I currently have a draft that's exited working group last call in the IETF for extending that reservation from being just DS Lite to including any IPv6 transition mechanism.
And the follow-up to that is that with an application like Skype, that it sees that IP on the handset and it sends it up to the server through its own protocols and stuff, and says other handsets or other devices can contact me at this IP. Obviously, that's not routable, or it's not going to get to that device. Is Skype like making connections out to something on the internet, and it's going through 464 XLAT and then through your carrier grade NAT, and you're ending up with an external IP somehow that it can detect through a server connection or something?
So I can't tell you how Skype works because I don't know, but I know that it functions. So I have to assume.
Awesome.
I have to assume they are treating this address as they would treat an RFC 19 address, meaning that they wouldn't communicate it as part of their peer-to-peer network, and that they would execute something like stun, where they would discover what the externally viewed IP address would be, and then use that as part of their proxying and connections and whatnot.
Cool. Thank you very much for your talk. It was excellent.
Thanks. Skype is so Skype and a lot of these other applications that we found couldn't work with IPv6 very well. They actually have a really great reputation for working over complicated networks. So we don't worry too much about Skype. They're very capable of getting multimedia through all kinds of interesting networks. So I think they'll be pretty good at succeeding.
All right, thanks a lot. Thanks. That's great.